ready, I'm gonna, yep, there it goes. All right, should have got a notification.
Yep, I got it.
All right. So for those of you who are following Digital Inclusion Week 2022 edition, this is our 4th presentation brought to you by Cam and Tracy Hughes from C-Test Labs. Thank you guys for being here.
Thank you.
Thank you.
All right. And do you guys want to say what you'll be presenting today, or is that in the video?
Yeah, well, I can give it a little bit of heads up. So this is really part 2 of a 4- or 5-part series on building an Arduino sensor agent. We gave part 1 last week. We did a talk on that, and this is a follow through on that talk. And so we introduced a little bit more in the video, but basically it's the second part in what will be a 4- or 5-part series.
Awesome. Well, thank you for being here. Thanks for being part of Digital Inclusion Week. And I'm going to go ahead and mute my mic. You guys take it away.
Okay, thank you.
No problem.
We use the intended audience matrix meter. This presentation is suitable for beginners.
Great to see you folks. Want to give a shout out to the folks out there from our RUR group, the Retro Underground Roboticists. Shout out to the Neo ACM people that are in the crowd and out there in the stream. Also, any of the folks from Oak Hill Robotics Makerspace that's watching this right now. Also want to give a big thanks to Oak Hill Collaborative for sponsoring and hosting the Oak Hill Robotics Makerspace. Without the folks at Oak Hill, Anthony Hake and Pat and the Oak Hill Collaborative group, we could not pull this series off. We also want to give a shout out to C-Test Laboratories. We're using a lot of their agent architectures and epistemic structures and things, technical robot designs, and the Rome Robotics Lab. So we want to give a shout out to those folks. And to the people out there that have been following us on the CSI Clue Robotics Challenge. We want to acknowledge all the folks out there, and anybody else, welcome that's get a chance to stop in and see this talk. We are live streaming this talk, but we're also recording it for those of you that won't have the opportunity to stay through all of it or listen to or see all of it. It is going to be recorded and it will be posted. And in fact, this particular one on design, it's a little longer than our normal 15, 20-minute talks. And so you probably will want to come back and revisit this talk again. And some of the information in it is going to be the kind of information that it doesn't all sink in the first time. And you have to listen to it again and maybe 2 or 3 times before it makes sense. Or maybe you need to be a little bit further in the project before things start to click. So I'm glad we're recording this, and I do recommend that you maybe not try to take all of this in at one time and that you pace yourselves on some of this stuff. Okay, so this is part 2 from in our designing Arduino sensor agent talk, where we are dealing with the Arduino meets the Raspberry Pi in a robotics project. It's going to be kind of fun, and we're designing sensor agents. And the first part, we more or less did an overview of the entire project and the kind of components. So for those of you that are just jumping in at this part 2, realize there is a part 1. and that has been posted, and you can gain access to that. And I do recommend that you watch that, because that's kind of a prerequisite for this part. We define some things in part one that won't make sense to you in part two unless you saw part one. So I encourage you to go check that out. So designing Arduino sensor agent, we get started with this thing and see what goes on. You know, why do we do design? Listen, we do design because we want the device or agent or system that we're building to do exactly, no more, no less, what we want it to do in some given scenario, right? It is very easy when you're dealing with the Arduino and Raspberry Pi. You know, those platforms invite you to experiment and tinker and, you know, and do stuff off the fly and in ad hoc ways. And so it's very tempting to do everything that you do in Arduino and Raspberry Pi in that way. But you can't really do that for things that you need to rely on, some process, some device, some system that you really need to rely on. You need to guarantee that the system performs properly each and every time, and that you get the correct results and the correct behavior each and every time. You cannot put that kind of system together in an ad hoc tinker, group, you know, I don't know what you call these things at this point, where we just all brainstorm and we use crowd wisdom and we come up with something really nifty. Okay, you can't design real systems that way, not reliable systems. And you, if you can, I don't want to know about it, and we certainly won't be doing it here today. We're into real design, and the kind of knowledge drops that we do involve things to help you, and tools and techniques to help you get things done for real. And so we do design because we're trying to get a very predictable and expected behavior in some given scenario, with the emphasis on the word scenario here. We want the device, the agent, or the system that we're building to perform a very specific, predictable, and expected way in some scenario, right? And so what do we mean by scenario? And this is one of those examples of the talk where I think you might have to revisit this aspect of it again, maybe multiple times in weeks and months to come, because this is kind of a dense set of definitions here, and you might have to read it and let some of it sink in, and then go away and come back and read some more and let a little bit more sink in, and go away maybe a month from now and then read it again. I'm placing a big emphasis on this. Tracy and I both want to place a big emphasis on this, because situations and scenario is a key part of the robot system and agent design that we espouse, that we promote. It's a key. And without a good grasp of what we mean by scenario and situation, you're going to be lost. So I'm taking the time now to put these definitions here, because we're going to use them over and over again, and we're never going to get away from them. And so if you don't like these two words, scenario and situation, I suggest you run now because they're not going anywhere, and they're key and they're essential to everything that we do. Everything that we do with respect to the Arduino and Raspberry Pi, or any agents, or any artificial intelligence, or any robots, or any embedded systems, all of those things are all relative to some particular scenario, some particular situation. And we only discuss those things and their capabilities relative to some specific scenario situation. And our designs, our situation tests, everything is relative to that. Okay, so if you get these definitions here, scenario being a sequence of events or a series of planned events that represents a shared or commonly understood or easily imaginable occurrence. Or you could look at it as a description of a sequence of events that could possibly happen. A description of a proposed or supposed sequence of events or actions that could easily be imagined, understood, or conjectured. Or you could look at it as a synopsis of possible course of events or actions that can be readily imagined or understood, right? So any of those, whichever one makes sense to you, they all basically mean the same thing. There are three different ways of describing what a scenario is. Understand at least one of them, all three of them if you can, because you need it. And so we have that as a scenario. And for our purposes, we break down a scenario into a discrete set of situations, okay? So for us, all scenarios can be broken down into a discrete set of situations. And what's a situation? It's a combination or collection of conditions, circumstances, and variables that hold at a particular moment within a scenario. Like I said, this has got to be the kind of stuff that you are going to you read it a little bit today, get a little bit of it today, and maybe, a couple of weeks from now, absorb some more, and it'll become clear and more obvious and maybe more pertinent as we go on here. I won't get into the state and model thing just yet. We'll save that for later. And I do want to say this, though. At some point, we will introduce the mathematical definition of scenario and mathematical definition of situation, because those are actually very technical terms and they have very specific mathematic definitions. We won't bring it up today, so no need to fret. And it may be months, maybe even next year before we bring that up, but it will get brought up. Okay. So in terms of design the agent, if you don't fully understand the scenario and the situation that could arise from that scenario in the design of your agent, then stop. Just don't go any further. Come back once you do fully understand the scenario and the situation that can arise from that scenario. That you're getting ready to get a machine or a device or a computational agent to perform something inside of a scenario with some set of situations. If we don't have a full understanding of that scenario and the situation that can arise, we don't need to be writing any kind of code or building any kind of system or wiring any kind of Arduino or Raspberry Pi or anything else until we do understand the total, have a pretty thorough understanding of the context that a device is going to be in. Okay, so if you don't have a grip, come back when you do have a grip. And then we kind of break that up into engineering and in software engineering. We kind of call that preliminary design versus detailed design. We want to make sure that you have a solid understanding of everything that's involved during the preliminary design or in the preliminary design phase. Okay, and I'm going to say, look, you cannot build an agent or a system that executes properly and safely in a scenario that we don't fully understand. You just can't do it. Okay, don't even try to do it. You wouldn't be able to prove that your system or your agent is correct. It will do the right thing under all of the circumstances or situations that can be presented with, and you won't be able to prove or show that it operates properly, giving you the correct answers or results, or you won't be able to show that it's safe if you don't understand the scenario that you're putting it in. Right? You can't show that something is safe or that it operates properly if you don't understand the scenario that it's going to be in. You just can't show that. If you guys don't believe that, see me at some later time, and I'll take the time out to explain to you why that's the case. There are three basic approaches, three tools that we use when we are doing our design. We use something called, we produce something called background knowledge tips. and something that we call a 5 diagram, and then we produce something that we call an agent system situation check. That background knowledge tips, that's a document. You can do that in a text editor, and what it does is it really lays out a pretty high-level overview and description of all of the things, individuals, and places in the scenario. So you take some scenario, like in our case, the scenario is we're going to be measuring soil on our own property, and then we're also going to be measuring soil at the Oak Hill Collaborative. So we're going to take soil samples from possibly the front of the location and the back of the location. We'll probably take soil samples from the front of our home and from the back of our home, and we're going to measure those soil samples to see how much salinity they have. That's an example of the scenario where taking soil samples from the front and the back of locations of a couple of locations, and we're measuring those samples for salinity. That's a scenario. And in that scenario, we have things like we have a conductivity sensor, we have an Arduino microcontroller, we have a veneer sensor shield. Okay, we have beakers, we have test tubes, we have things, and so we need, those are examples of things in the situation. Tracy and I are the roboticists, and we're going to be actually working with the devices. We may work in conjunction with Anthony Hake. We might need his permission, or we might need Pat's permission to take soil samples. So he would be in the scenario. The places that are involved, my personal home, Oak Hill Collaborative, those are the places. So we have the things, we have the individuals, we have the places, and we take note of that. And we put down relevant, we describe and document relative information, background knowledge that it might be needed in the process of putting this project together. We call those background knowledge tips, okay? We can do that with any kind of text editor. The 5 diagram is a diagramming technique that we've come up that gives us a visualization of our design and what things are going to look like and what we're going to need, what the inputs are going to be and what the outputs are going to be and what the processing is going to be. And we kind of draw all of this out, and we do all of this in a drawing or diagramming program. We happen to use something called, for all of this, we happen to use something called OpenOffice or LibreOffice. This is a free software that you can download that's available for Windows, Mac, or Linux. I highly recommend LibreOffice. It's very robust, very feature complete software. In anything that you need to do in a design phase, believe it or not, you can get it done in with this software. And so if you don't have anything particular, I recommend that LibreOffice, and that's with Libre Office or OpenOffice. And for those of you out there using Solaris, Star Office, it works, actually is works pretty good, it's pretty compatible. And then the last thing that we do is what we call agent system check, and we do that with the spreadsheet. And so the 5 diagram is a visualization kind of thing that lets you see visually what things look like. In the agent system situation check, you'll see is an expectation versus delivery type of analysis that we do in our design. And so for an example of the things, capturing the things, we talked about a conductivity sensor. And what do we mean by a background knowledge tips? If the conductivity sensor is one of the things that we're talking about, then the background knowledge for that conductivity sensor will be the specifications. If you're using a sensor, you need to understand what its specifications are, what its capabilities are, what its limits are, what its strengths and weaknesses are. Our particular conductivity sensor operates in 3 ranges. It has a low, mid, and a high range. It has a response time. It talks about the temperature compensation, and it has a temperature range that it operates in. You don't want it to be under 0 degrees Celsius. You don't want to be over 80 degrees Celsius, you know, or you're going to have problems. You need to understand what the specifications are. You look at this spec sheet here, and if you don't understand what that move signal is, what the S slash centimeters, micro, you know, if you don't understand what microseconds per centimeter, or, you know, what's this, you know, 100 milligrams per liter TDS, I think that's total dissolved solids. You know, if you don't understand what all that stuff is, stop. Go away, come back when you do understand it. Look it up. Understand what the capabilities of the devices that you're working with, what their limits are, what their safe operation is, what their function is. That's when we say tips, background knowledge. Part of the background knowledge for the conductivity sensor is this specification sheet. You want to make sure that you got a good grip on something like that. Here's the Arduino. Wow, you know, look at these, you know, we've got these pins, and we notice that it has digital pins and that it has analog pins, and you know, it's got a USB port on it, and there's a 5-volt power supply. You need to understand what you're working with. We're working with an Arduino Uno as opposed to a Nano or some other kind of Arduino. You need to know what that is, what kind of microprocessor it is. Wow, there's a serial port and a right there, our TX and our RX. You need to know what this is. Can you use the Arduino without understanding what the Arduino is as a user? Yes. You know, there's all kind of nice, cool Arduino, simple projects that you can use and put together without very much understanding. If you're the person that's developing some kind of project and an embedded system that you want to use the Arduino in, and if you expect that Arduino to be reliable, dependable, and safe, you do need to understand what it's capable of and what its limitations are, period. If you're the programmer, you're the engineer behind, you don't get to behave like a common user. You have a little bit more responsibility, okay? And so part of that background knowledge tips is understanding, this would be an example of one of the things in the tips, that T for things. The Arduino itself would be one of the things. And this is, again, Arduino has a spec sheet, okay? It has, 6 analog input pins, 6 digital pins. You need to know that. It does not have 12 digital pins, right? Sometimes that people believe that, for I don't know why they believe that, right? It's not a multi-core device. I don't know why people believe that either, so you need to understand what it's capable of, and the background tips and the background knowledge for the things involved in the project are necessary for the design. These things all impact the design. I can't ask the Arduino to accept 7 analog values when it only has 6 analog pins, right? And so you can't ask it to do a certain task at a certain amount of time if its clock speed is limited to 16 megahertz, right? You can only process so much information at a time, and you need to know what that limit is, right? You need to know what the voltage, operating voltage is, right? And, do I want the input voltage to be, is it okay for the input voltage to be 3? Is 3 volts fine? What about 19? What if I only have, what about 12 and a half volts or 13 volts? Am I good there? And what happens if for some reason we get 25 volts in Arduino? I'm going to fry it. If I get 2 volts in Arduino, it's going to be a brownout. Am I going to jack up my project because the voltage is wrong? You need to know these things if you're really going to build something and design something that works and is reliable and it's safe. And so that's what, when we say background knowledge tips, this is the kind of things that you want as a part of your design. Okay, and so here's a part of what we call an IPO chart. We just did this in one of these drawing programs. And it's just basically a table that breaks down the input, the processing, and output. And in this case, this is a simple example of operation 1. So that conductivity sensor has 2 basic operations. It can do measurement. The sensor can measure something, or our agent will be able to measure something, or it will be able to calibrate the sensor. So there's 2 basic operations our Arduino agent will do. One is measurement, the other one is calibration. What this IPO chart an IPO, input processing output, that's what that stands for. What it's basically showing is the basic high-level view of what that measurement requires. So in order to perform that measurement or with the conductivity sensor, you need to know the slope and the intercept. And if you don't know, if we haven't decided what operation we want the agent to do yet, you need to tell the agent which operation to use. So it could be operation 1 or 2. Operation 1 is the measurement. Operation 2 is the input, is the calibration rather. And it could be, you may need to, if it's operation 1, you need to supply the slope and the intercept. Now, what's the slope and the intercept? Well, if you did the background knowledge tips for the conductivity probe, you know what the slope and intercept is. So I'm not going to even share that with you right now. Well, we will share, but we'll share that at a later time. And the processing is just a high-level set of activities that we know the agent is going to do. It's going to read that analog sensor. You know, when you get ready to measure something with that conductivity probe, the sensor that we have is an analog. It's not digital, it's an analog. And so we need to get an analog reading. We're going to take that reading and we're going to do a simple multiplication and division there. It turns out that the Arduino analog pins deliver values from, you could look at it from 1 to 1024 or from 0 to 1023. But basically, you get values in that range. And then once we get that value, we calculate what the conductivity is. And then the output from that the agent is going to send back to us. The agent is going to send us the status code letting us know if everything is okay or if something failed. And if something failed, what failed, and what kind of problems it had or what kind of success it had. And then it's also going to give us the conductivity reading if it was able to make a reading, right? And so this is what's called an IPO chart. And this is the IPO, a simplified one for the purposes of this, our little talk today for operation 1. And operation 2, which is the calibration, let's just say the sensor is not, it seems to be off and it needs to be recalibrated. Well, this is the process that the agent would use to recalibrate that sensor. If you remember, we said that the agent can only do 2 operations. The agent is going to be able to take a measurement for us, or the agent will be able to calibrate the sensor for us. The IPO chart that we just saw was for the measurement. This one is the process for the sensor. And what it does is you give it what you expected the value to be, and the agent looks at what the actual value is, and then it calibrates the sensor so that the actual value matches the expected value. And what it gives you in return at the end of the process is a new slope. So remember in the previous IPO chart, slope was one of the inputs. Well, if you needed to recalibrate the conductivity sensor, you would ask the agent to do a calibration, and then it would give you a new slope, and you would use that slope to put into the operation measurement that we showed on the previous slide. So this is just an example of what this design looks like. You do this before you write any code, before you look at any C++, before you look at the, the setup loop in the Arduino or the loop, the setup method function or the loop function in Arduino. You do this part of the design so you'll know exactly what the agent is going to be doing before you write any code. You also lay out all your data. The data that you're going to be sending to the Arduino, you want to know what format that's in, and the data that the Arduino is going to be sending back, you want to know what format that is in, and you decide that layout ahead of time. You don't decide that layout on the fly. You decide that layout on ahead of time. In this case, this is what the format that the Arduino is sending back to us. The agent is going to send us for operation 1, it's going to send us a string where the items are separated by commas. And in this case, the first thing is in the string 1 is going to be the number of arguments it's about to send. It's going to send that status code, and it's going to send back the measurement. And the sentinel is just a character that you put at the end. You know, if you have a comma separated string that you're sending, and we don't know how many things are going to be in that string, if you put a sentinel at the end, you can tell who's ever receiving that string to look for the sentinel, and that's how you'll know what the end, you received the end of the transmission. And in our case, the end of the transmission is going to be a pound sign. Okay, so we got for operation 1, which is the measurement, the agent basically sends you back the measurement and a status code. And for operation 2, which is the calibration, the agent sends you back a new slope and a status code. And if the status code is an error, then you know you can ignore the measurement and the slope, right? And if it is an error, our status code will tell you what went wrong with the measurement or what went wrong with calculating the new slope, okay? And this is the data format for what you would send to the agent to have it start to do some work for you, right? Tell it which operation you want. That's whether you want the measurement or whether you want the calibration. And if it's the measurement, then you send the slope and the intercept. And if it's the calibration, you send expected value and the actual value. You lay this data out in a design aspect of all of this. And then when you get ready to do the coding, you'll know what it is that you are going to be receiving and the format of what you're going to be sending. Laying this stuff out right now at this point helps you design your classes and your objects and all of those things properly. You know, you're not designing those as you go. And when you do it this way, you're going to see that you end up with a better object-oriented and agent-oriented design. So lay it out ahead of time. This is an example of a flow chart. And for those of you who don't know what flow charts are, okay, I'd Google those. This is a way of visualizing the logic of your program, the set of instructions that you expect the agent to execute. This is a visualization of those instructions. And you know, the one that I like in this diagram is the diamond near the bottom where it says sensor and range, right? If the sensor returns a value that's not in the correct range, I want to know about it. I want some kind of error code to be generated. I want the program to alert me that the sensor measurement was wrong, or the result was wrong, or something is goofy some kind of way. I don't want it just to send me back the value and I think that value is useful and then I run with it, right? We don't want to do that. And so part of this visualization of the logic lets you see what instructions you expect the agent to execute. And if the agent cannot execute those instructions, what do you want it to do? Or if the agent gets a result and the results are not acceptable, what do you want the agent to do? Or what's the state of affairs? Okay. And so we're going to talk a lot more about these flowcharts as we go through the weeks and months on this project, because they're central. We use them in the design. It lets us do the design without running code and without having to write code. And, you know, it's easier for us to see what those set of instructions are. And they're very easy to generate. I mean, if you have something like OpenOffice or however whatever software you use to do flowcharts, you get in the habit of using those, and then you'll see how useful they are in the design process, right? Here's another example of a little more of the 5 diagram for our connectivity sensor. In this case, for those of you that are familiar with Arduino programming, you know you have 2 functions. You have a setup function, and then you have a loop function. This particular part of the flowchart is visually describing the loop function for our conductivity sensor agent, right? The first thing we do is, well, actually, it starts off with the initialization. So it does call the setup function there. You see when it says initialize setup connection, that's going to be something that happens in that setup function. And if we are able to establish the serial connection, we continue on to the loop. And if not, then we return a status error. You can see that we get the request string. We check to see if that string is in the correct format. If it's not in the correct format, for whatever reason, maybe the data was corrupted when it came in, or somebody hacked it, or for whatever reason, the data is not correct, a status code is set, and we go to module D. And module D actually is just another flowchart that basically sends back the state of the system. And if the string is correct, we check to see whether we want to do operation 1 or operation 2. If we want to do operation 1, and we go to module B, that's another flowchart off screen. I'm just showing you a subset of this here for this, and I'm trying to keep this talk short, right? It's hard to do with so much stuff. But again, some of the stuff is dense. And because it's dense, we're making sure we record this stream, and you guys are going to be able to refer back to this and look at this up close. And so if we want operation 1, then we're going to go to module A. And if we don't want operation 1, that means we want operation 2, which is the calibration. Then we'll go to module B. But this thing lets us visualize what that logic looks like ahead of time. And then remember what I said, that the 5 diagram is a combination of things, of all of these different diagram methods. So on a real 5 diagram, not only do you have like the data layout that you see right here. So you see where it says receive format and send format. These are the data formats that you're going to be using in this project for that connectivity probe, and that we'll be using. You're going to see what this looks like. We have 2 receive formats depending on whether we're talking about a measurement or a calibration, and we have 2 send formats, which is this is what the agent sends back to us, depending on whether we have a measurement or a calibration. Okay, and on the same diagram, we have the IPO chart and the for the operation 1, and we have the IPO chart for calibration 2. And on this same diagram, if I wanted to scroll the screen right now, because you'd be able to pan this, it's a pretty big diagram, you'd be able to see the flow charts for all of this. And a 5 diagram lets you put everything in one place, right? So you can pan around and see what it all looks like, okay? But this is all part of design. And you lay all of this stuff out long before you do any coding or any wiring, because you want to know at the design phase, will your approach, however you're getting ready to put this agent together, will it actually give you the results and behavior that you expect each and every time? And you can only guarantee that if you have a thorough design, right? And last, this is that system situation. And notice, check, meaning that I want to come up with all of the situations within our scenario that our agent could face, every single one of them. If there are only 2, I want to list 2 of those situations, what I expect the behavior to be in both those situations. If there are 2,000 situations that our agent may be in, I want to list all 2,000. And in each of those 2,000 situations, what do we expect for our agent to do? Now, here's an important point. You want to make sure that you are aware of every single situation your agent can be in within the scenario that has been defined for. Every single one. And you want to know how that agent is going to behave in every single one. And you want to know that the behavior of that agent is going to be correct and accurate in every single one, right? And so that's the purpose of this system situation check. You come up with the situations. In this case, I only have 12 situations that we want to check our connectivity sensor for. Look at the test data. Remember we said the data layout, and that 4 stands for, lets us know that it's going to be 4 bytes, four pieces of data rather coming. The first piece of data is going to be the operation type, which is a 1. So this let me know it's a measurement. That next one is the slope. And that third one is the sentinel, it's the pound. So there's 4 arguments altogether, including the first one, right? So, and notice that there's 3 commas here. That's this. Programming will help you if you know about programming. We can determine how many arguments we have in a character separated a string by counting commas, or whatever the delimiter is. But in this case, we're going to give the connectivity sensor 4 or 3 different pieces of data, and we're going to have it do that data. We're going to give it 4 pieces of data, and we have it do that data for 3 different ranges, right? We're going to have the sensor measure distilled water in all 3 ranges. We're going to have it measure tap water in all 3 ranges. We're going to take a calibration measurement in all 3 ranges. And then we're going to have it measure a gram of magnesium sulfate and 100 milliliters of tap water in all 3 ranges. And magnesium sulfate, for those of you who don't know, is just Epsom salt, common Epsom salt. So it's not like bomb making material or anything. If you get it in your eyes, you don't want to do that. And you don't want to like take a handful of it and swallow it or anything crazy like that. You don't want to rub it in a wound or anything. We'll talk more about material data safety sheets. But in any case, we're going to put this connectivity sensor in 12 situations, and we want to know what it does in each situation. We have an expected result, and we want to make sure that the actual result matches that expected result, okay? So notice for number 3, we have question marks there. That means we don't know what our expected result is for that, which means that we can't finish this part of the design until we do know what those things are, right? If your design is incomplete, don't start writing any code. Don't do any wiring. Don't do any welding or soldering or any rest of that stuff, until you have a complete design, until you have a complete understanding of the scenario and the situations that can arise in that scenario. Don't get to the actual details of this thing yet. I'm going to apologize for this long talk. I didn't mean to go so long today. And I tried to make the stuff as brief as I could, maybe too brief in one instance, and not long enough in another instance. It is going to be, like I said, we're going to post this talk, and we're going to make ourselves, we will be available for those of you that have questions that want to go deeper into this and go through any aspect of this and drill down into it. We will be available. You can either contact us through email or make arrangements to meet up with us at Oak Hill Collaborative, the robotics makerspace down there. And we'll be more than happy to take as much time as you want to talk about any aspect of today's talk, because this is our thing. This is what we do. I'm going to call it a day right there. That's it. We're going to make this the end of part 2, designing an Arduino sensor agent. Next time, we're going to drill down a little bit more in design. We'll talk about the UML and how that applied to designing the class of the sensor agent, the methods. We get a little bit into material data, safety data sheets, and how those apply to this particular project. And we'll drill down into the architecture of how we come up with the attributes and the methods of our C++ class and our Arduino environment. We're actually going to walk through the code as much as we can. And I will try to keep that one short also. But we are going to show what it looks like to design to code an agent on a reflex agent at the very least on an Arduino. And we're going to get into that for part 3. So folks, thanks for persisting through all of this. And again, thank you, Oak Hill. Thanks for everyone that watched the stream, and we'll see you guys next time.
Wrong camera. All right, that was a good show.
Hey,
Let's see here.
Made it through.
All right, and I'm gonna go ahead and
If
stop
there are any
the live
questions,
stream.
we can take-
Everyone who's watching at home, thank you for tapping in. This has been the 4th talk of Digital Inclusion Week. This is Agent Sensors with Cam and Tracy Hughes from C-Test Labs. Thank you, guys.